This is the F-22 Raptor, an aircraft designed to do something that sounds almost contradictory. It can fly faster than the speed of sound without constantly pouring fuel into afterburners, turn with astonishing agility at extreme altitude, carry its weapons inside its body, and appear far smaller to radar than a conventional fighter of similar size. In raw dimensions, it is about 62 feet long, with a wingspan of 44.5 feet. Yet, what makes it extraordinary is not just what you can see. It is what has been hidden inside that shape. Because the real story of the F-22 is not simply that it is fast, stealthy, or advanced. It is that engineers took several of the hardest problems in fighter design and solved them all at once. So, how do you build an aircraft that can hit like a heavyweight, move like a knife fighter, and remain incredibly difficult to detect? To answer that, we need to go inside. The F-22 was born from a brutal design challenge. During the Cold War, military planners were looking beyond the fighters already in service and asking a dangerous question. What happens when future air combat is no longer decided by who can turn tighter in a dogfight, but by who sees first, shoots first, and survives first? Existing fighters could be extremely capable, but they were still based on trade-offs. A plane might be fast but visible, agile but fuel-hungry, powerful but overloaded with pilot workload. The next generation would need to defeat advanced radar networks, operate in contested airspace, and outmatch enemy aircraft before the opponent even knew the fight had begun. That problem became the foundation for the Advanced Tactical Fighter program. In the late 1980s and early 1990s, competing prototypes were built to prove whether this impossible wish list could actually be turned into metal, composite, and software. The YF-22 and YF-23 represented two different paths into the future. One emphasized a certain kind of stealthy efficiency. The other offered a balance of stealth, agility, and operational flexibility that ultimately won the competition. The YF-22 was selected in 1991, and what followed was years of engineering refinement to turn an experimental idea into an operational machine. The first development flight came in 1997. Initial operational capability arrived in 2005. That timeline alone tells you something important. The F-22 was not created as a single invention. It was assembled from thousands of solutions to thousands of separate problems. And physically, it is a fascinating machine. Empty, it weighs more than 43,000 pounds, which is roughly the weight of a large city bus. At maximum takeoff weight, it can reach around 83,500 pounds, pushing into the territory of something that feels far too heavy to behave with grace in the sky. Yet it does. Its ceiling is above 50,000 feet, where the air is thin, the margins shrink, and performance becomes harder to maintain. Its speed sits in the Mach 2 class, but that number only tells part of the story. What really matters is supercruise, the ability to sustain supersonic flight without relying on afterburners in the same way older fighters do. That means it can move faster over meaningful distances while burning less fuel than an aircraft that needs its engines in full, fiery excess the whole time. It is the difference between a sprinter who can briefly explode with speed and an athlete who can hold impossible pace mile after mile. But the F-22 is not impressive because it is one thing. It is impressive because it combines things that usually fight each other. Stealth wants shapes that reduce reflections. Maneuverability wants control authority and aerodynamic freedom. Speed wants thrust and efficiency. Internal weapons storage wants space. Range wants fuel. Sensor power wants electricity. cooling, and integration. 5. Every one of those demands pulls on the design in a different direction. That is where things become even more interesting. The F-22 is really a machine for reconciling contradictions. Step closer to the nose, and the first layer of that logic appears. The front of the aircraft is not shaped simply to cut air. It is shaped to manage what radar waves do when they strike it. The angles, edges, and surface alignment all matter, because radar is not magic. It is energy. If that energy is bounced back directly to the source, detection becomes easier. If it is scattered away, absorbed, or prevented from producing a strong return, the aircraft becomes much harder to find and track.
On the F-22, this principle shows up everywhere. The planform alignment, the carefully controlled edges, the buried internal bays, and the way surfaces meet one another are not styling choices. They are part of a geometric strategy. Inside that nose sits one of the aircraft's most important hidden systems, its radar. And this is where the story takes a turn. Many stealth discussions focus only on invisibility, but the F-22 was never meant to be merely hard to see. It was designed to see first. Its sensor suite, including its powerful radar and integrated avionics, helps create a fused picture of the battle space for the pilot. In older aircraft, a pilot might be forced to mentally stitch together data from multiple displays, warning systems, radio calls, and separate sensors. In the F-22, much of that burden is reduced through sensor fusion. The aircraft is not just collecting information, it is organizing it, prioritizing it, and presenting it in a way that helps the pilot act faster. That may sound less dramatic than speed or stealth, but in modern air combat, clarity can be as decisive as thrust. Move into the cockpit, and the philosophy becomes unmistakable. The F-22 has only one crew member. Means the entire machine has been built around reducing workload while increasing awareness. The pilot is not there to manually manage a chaotic pile of independent subsystems. The aircraft is designed to act as an integrated combat platform. It is one of the Raptor's quiet revolutions. It is not only a fighter with advanced parts, it is an aircraft whose parts were built to think together. However, the real secret lies elsewhere, because gathering information is only one side of the equation. The aircraft also has to survive while carrying that information deep into dangerous airspace. Now move to the center of the jet. This is where the Raptor starts to reveal how seriously it takes stealth. Instead of hanging missiles and bombs under the wings, where they would create drag and strong radar reflections, the F-22 carries its primary weapons internally. In air-to-air configuration, it can carry 6 AIM-120, AMR-AMS, and 2 AM-9 Sidewinders. In air-to-ground configuration, it can carry 2 1,000-pound JDAMs internally while still retaining air-to-air missiles for self-protection. That arrangement is a major clue to how the aircraft was meant to fight. The F-22 is built to preserve its aerodynamic cleanliness and low observability for as long as possible, then open its weapon bays, launch, and close them again in moments. At first, this seems simple. Just put the weapons inside. But engineers solve that problem in a remarkable way, because storing weapons internally means creating room inside a body that also needs fuel. Structure, avionics, landing gear, environmental systems, and massive air channels for the engines. Space inside a stealth fighter is some of the most contested real estate in aerospace engineering. And then there are the engines. Two Pratt Whitney F119 turbofans sit deep inside the aircraft, each in the 35,000-pound thrust class with afterburner. Together, they give the F-22 more than brute force. They give it options. High thrust means rapid acceleration, strong climb performance, and the energy to sustain aggressive maneuvering. But that is only part of the story. The engine installation is deeply tied to stealth, thermal management, inlet design, and signature control. The air intakes have to feed those engines efficiently across a wide flight envelope, while also helping conceal critical compressor faces from radar. The exhaust has to generate immense thrust while contributing to the aircraft's overall low-observable strategy. Every square inch around these engines is part propulsion system, part thermal problem, and part signature management puzzle. Then come the nozzles, and with them, one of the aircraft's most recognizable engineering tricks. The F-22 uses two-dimensional thrust vectoring nozzles. Instead of simply blasting thrust straight backward, these nozzles can redirect the exhaust stream in coordination with the flight control system.
That gives the aircraft extraordinary pitch authority, especially at high angles of attack, where conventional aerodynamic surfaces begin losing some effectiveness. In simple terms, the jet can point its nose in ways that look almost unnatural for something of its size and weight. But here again, the important thing is not showmanship. Thrust vectoring helps the pilot control the aircraft in extreme flight conditions, recover energy intelligently, and maintain combat positioning. It is not there to make the airplane dramatic. It is there to make the airplane dominant in parts of the envelope where lesser designs start to run out of answers. So this brings us to the core question. What is the F-22's most unbelievable capability? It is not speed alone. It is not stealth alone. It is not radar alone. It is the way the aircraft compresses the entire chain of detection, decision, and action, while making that chain harder for the opponent to interrupt. That is the real magic of the Raptor. It shortens your timeline and stretches the enemies. Here is how that works in practice. First, the aircraft enters an area where detection is dangerous. Its low-observable design reduces the chances of being seen early or tracked effectively. That buys time and space. Next, its sensors begin building a picture of the environment. Radar contacts, possible threats, positional awareness, and targeting information are fused for the pilot. Then, because the aircraft can supercruise, it can reposition rapidly without the same dependence on afterburner that would otherwise increase fuel consumption and signature issues. That speed is not just transportation, it is tactical freedom. After that, if engagement becomes necessary, weapons can be launched from internal bays while preserving the aircraft's core design advantages for as long as possible. Finally, thrust, aerodynamics, and flight control authority allow the aircraft to maneuver aggressively if the situation collapses into a closer fight. Input, system, reaction, process, result. Reduced detectability leads to earlier awareness. Earlier awareness leads to better positioning. Better positioning leads to first shot opportunities. First shot opportunities reduce the need for risky close-range survival. The aircraft is not just performing well in separate categories. Each capability amplifies the others. That synergy is why the F-22 has been described in terms like first look, first shot, first kill. Strip away the slogan, and what remains is a serious engineering concept. Win before the fight becomes messy. Shape the engagement before the opponent can fully shape it back. From a design perspective, that is brilliant because it means the aircraft is not relying on one miracle feature. It is relying on the compounding effect of many advanced features working as one. And yet, stealth remains the most famous piece of the puzzle. People often imagine stealth as a cloak, as if the airplane becomes invisible. It does not. Stealth is really the art of reducing opportunities for detection and targeting across multiple domains. Shape matters, materials matter, edges matter, gaps matter, maintenance matters. Even preserving the aircraft's low observable condition requires specialized work. Because stealth is not just designed into the jet, it has to be sustained throughout its life. That is why supportability and coating repair became such a serious part of the F-22 story. A stealth aircraft is not only an aerospace product. It is an aerospace product with a maintenance philosophy, built around preserving its signature advantages. And that leads to a surprising reality. One of the most advanced fighters ever built is not defined solely by glamorous performance numbers. It is also defined by logistics, reliability, repairs, and modernization. Lockheed Martin has described ongoing upgrades intended to help the F-22 to see farther, go farther, and shoot farther, while sustainment programs manage tens of thousands of parts across the fleet. In other words, even a revolutionary aircraft has to survive the ordinary reality of service life. Parts wear out. Coatings need attention. Software evolves. Threats change.
The Raptor's long-term significance comes not only from what it was on day one, but from how its architecture has been adapted to remain relevant. In the real world, the F-22's importance is strategic as much as technical. It is an air dominance fighter, meaning its central role is to secure control of the sky so other aircraft and forces can operate more safely. That matters because air power is never just about the airplane at the front. It is about everything that becomes possible behind it: surveillance, transport, deterrence, strike missions, and freedom of maneuver for entire joint operations. The Raptor was built to open doors in places where modern defenses try to slam them shut. But it also has limits. It is expensive, complex, and produced in relatively small numbers. Its sophistication comes with demands in maintenance, upgrades, and fleet management. That, too, is part of the engineering truth. Pushing to the frontier is rarely cheap or simple. Still, the F-22 changed aviation in a profound way. It proved that a fighter could combine stealth, sustained supersonic performance, super maneuverability, and sensor fusion into one operational platform. It pushed the conversation away from raw speed alone and toward integrated advantage. It showed that future aircraft would need to be less like standalone machines and more like intelligent nodes in a larger combat system. In that sense, the Raptor did more than redefine a category. It helped define the logic of modern air combat itself, and perhaps that is why the F-22 still feels so compelling. Not because it is merely powerful, but because it embodies a deeper engineering ambition to take a set of impossible demands and make them work together in the real world, to shape metal around physics, software around human decision-making, and performance around survival. It is a machine built not just to fly, but to alter the terms of what flying into danger can mean. The F-22 Raptor is, in many ways, a portrait of American aerospace engineering at its most uncompromising. A stealth airframe wrapped around sensors, engines, weapons bays, coatings, software, and systems that all had to be balanced with extraordinary precision. A fighter that looks sleek on the outside because it is solving incredibly messy problems on the inside. And the more closely you study it, the more remarkable it becomes, because hidden behind its sharp lines is an entire philosophy of speed, awareness, survivability, and control. And that is what makes the F-22 more than just another fighter jet. It is a flying answer to one of the hardest questions engineers can ask. How do you dominate an environment designed to find, track, and stop you? The Raptor's answer was not one invention, but a symphony of them. If you enjoyed this exploration into one of the world's most fascinating machines, subscribe for more deep dives into aerospace engineering, military technology, advanced aircraft, and the breakthroughs that keep redefining what seems possible.